Hello everyone, so today we are going to discuss the divide and conquer approach used in finding the majority elements in a particular array of size n. So first we will go through the definition of majority element. As we all know, a majority element is that element in a particular array who has an occurrence of more than or equals to n by 2 occurrence in that particular array. So coming to various approaches of finding the majority element, the first thing that comes to our mind is using a frequency array map. In C++, we can use an unordered map, in Python, a dictionary, or an array map in Java. This is going to give us a time complexity of O of n. As per our implementation, it can also be O of n plus n. If we run the loop twice, that is once on the map and once on the array, and it's always going to give us a space complexity of O of n that is going to be the size of the map which we are using. The second approach is the best approach that is used to find the majority element. That is the Boyer-Moore's voters algorithm with a time complexity of O of n. Then the third approach, which is not as good as the Boyer-Moore's voting algorithm, but it is good for visualizing the divide and conquer approach and knowing and how to get the recurrence relationship to find a particular time complexity of an algorithm which is recursive. We are going to learn the majority element using divide and conquer approach, which is going to have a time complexity of n log n, which we are going to discuss how we get to that particular time complexity below. So first, as you can go through that algorithm by pausing the video. So first, initializing the array, pair the elements in the array in the pairs of 2, and then if number of elements are odd, you will be left with one single element, and check if that left out element is the majority element, and if that majority element, just return it as the candidate which is the majority. Or after that, if it's not found as a majority element, now loop through the pairs and discard the pairs which don't have the same elements. And if the in a pair they have the same element, you have to discard the first element which is going to be similar. Then we are going to call the function again for the pair r's, unless and until we are left with a single pair as shown in the diagram here, 7 of 5 of 5. Let's run through this diagram. So I have taken an array of size 11, and so the majority element will be that element which is going to be greater than 11 by 2, that is going to be 5. First, as you can see, we have paired it as 7 7 5 2 5 5 4 5 5 5, and the last element is going to be 7, which is going to be left out as we have the odd number of element, that is 11. So it's 7 7, so we are going to remove the first element as they both are similar and put it in the pair in the new array, not the pair. This is the new array which is going to be formed, and this 5 and 2 is dissimilar, so we discard it completely. Then we are going to come to the 5 5. They both are similar, so we are going to give one of the 5, that is here. You can see one of the 5 is written below. Then 4 5, both are dissimilar, so discard it. Then another 5 5, both are similar, so keep one of them. Here you can see 5. And at last there is a 7, which is a left out one from the odd number of elements. We checked it with the count, that is 7 7 5. The number of 7s in the original is 7 1 2 and 3. The 3 is not greater than or equals to 5, so it's not the majority element, discard it too. So now we are left with a new array that is 755. We are going to call the recursive function again on it, and the recursive function in the second iteration will give this pair, that is 7 5 and 5. Again we are going to check for 5, but before checking for 5 we can also check for the 7 5 by looping on it. And once we have checked for 7 5, we see that they are dissimilar, so we are going to discard it. And then we have 5. We will check the 5 in the original array count, that is 1 2 3 4 5. As you can see, it perfectly fits the condition of having a majority element, so we are going to return it as the majority element. So this was the dry run. Coming to the pseudocode, where we are going to infer the time complexity using the recurrence relationship using the substitution method. There are three different methods which are particularly important to know: substitution, recursion tree method, which is a diagrammatic approach, and the third one is going to be the master theorem method. You can directly use the substitution method, and as a proof of proving that the substitution method is true, you can also use the induction method, but I have not discussed the induction method over here. I have just used the substitution method to just show you that this time complexity can be inferred as n log n for this particular algorithm of divide and conquer for finding the majority element. So first we are going to calculate the length of the array, then we are going to initialize the new array as pairs, and we are going to run a loop through the whole of the array. So instead of directly creating the pairs like pair of 1 2, that is two elements each, we are going to directly use we are going to have it dynamically, so we don't need to create two different arrays and two different loopings. and we can do it in a single loop using the visualization of the pair as array of I and array of I plus 1, that is its next element. So if array of I is equals to array of I plus 1, we are going to put one of the elements in the new array and we are going to increment it by 2, which means that we have seen through the first two elements, we have seen through the two elements, seen through the two elements, and going to the else condition where they are dissimilar, we are going to discard that element and we are incrementing it just by 1 because the next element of the after I may have another element of I plus 1 which may be similar to the other element so that we can put it into the new array. That's why we are incrementing it just by 1. Then we are going to call again the selection problem, selection a function over here. So it's going to divide it into smaller and smaller elements of n, smaller and smaller pairs, or you can say the arrays of n by 2, resulting in a small array of just either one pair or one pair and a single element. And that's how it's going to return a candidate. Then we are going to count that candidate count. And once that we are going to check if that candidate count is greater than or equals to n by 2, we are going to return the candidate or we are going to directly return n minus 1. And that's how the pseudocode works. Now coming to the inferring of the time complexity, as you can see, the first thing is that we are going to run a loop of while of n. So while running, we are going to incur a cost of c of n, where c is a positive constant. And then for again calling the recursion stack with n by 2 elements, as we are going to discard around n by 2 lesser than or equals to n by 2 elements at each iteration. As you know, we are going to either discard it. So for example, the worst case is going to be when we are going to have n by 2 elements at each iteration. This is going to happen if we have all the elements similar. So example, you can see I'm tabbing over here, that is 5, 5, 5, 5. So here you can see if I run the first loop, I will be getting 5 and 5 for my next iteration. As you can see over here, the 5 and 5 will be paired once, this 5 and 5 will be paired once, and I'm going to discard 1 5 from here and 1 from here. I will be left with an array of size n by 2. That's why I have chosen the worst case partition of n by 2, and therefore I have a cost of n by 2. And the best case would be that we are going to have a pair of 5 and some other element, that is dissimilar elements in all the pairs, and then we are going to discard all the pairs and we are left with 0 elements. And then coming to the another loop where we are going to keep a count for the candidate, which will be counted as a cost of c of n. So we can infer the time complexity or running time complexity of t of n equals to t of n by 2 coming from this recursion call, and the cost of combining the solutions as c of n. Actually, it's going to be 2c of n, but we can take this 2c is equals to one of the constants as c. We can write it as c of 1 or just c for simplicity. And then we can directly expand it using the substitution method. T of n by 2 will be substituted as t of n by 4 plus n. We have discarded the c for simplicity, and then we can again expand the t of n by 4 to t of n by 8 plus n, and we can generalize this in the form of 8 can be generalized as 2 to the power 3, and the 3 of n is already written outside, so we can substitute the k is equals to 3 over here and we will get the formula of 2 t n by 2 plus k of n. Then we can substitute n equals to 2 of k, as we want to discard the t of n element, that is the running time complexity for input size n, and we ended up by putting log on both the sides. We can get the value of k, that is k is equals to log of n, and when we put it we get that it's equals to t of 1. T of 1 is generally equals to 1, so we'll discard it, and finally we are going to left with a running time complexity of 1 plus n log of n, and we can infer from it that as 1 is pretty insignificant as a constant in a running time complexity, we are going to discard it and we are going to generalize it into time complexity of n log n. So I hope you like it, and please give suggestions to improve. Thanks.